Hi everyone, this video is on exercise 9I question 8. We have the function tan x and we want to prove that f of x has exactly one point of inflection at the origin. So they're basically telling us that the point of inflection here is the origin. We just need to prove that. So the first thing in questions that are about the point of inflection is finding the second derivative of the function. In this case, we need to differentiate the function f of x. So f dash x is equal to tan x differentiates to sec squared x. This is one of those standard results that I've also shown how you can get sec squared x in case you forget that it's sec squared x. So you can then differentiate that directly. It's just basically to tell you very quickly in case you don't remember the direct way, because we know that tan x is basically sine x over cos x. So we know this. And then hopefully you know the derivatives of sine x and tan x, so you can just use the quotient rule to differentiate this, and then you will get sec squared x. So that's the direct way of doing so. Now the second derivative needs us to both use the chain rule and also remember another standard result. The other standard result that we need for the second derivative is that sec x differentiates to sec x times tan x. Again, you can also differentiate this directly. Sec is equal to 1 over cos x, so you can just differentiate that using this the quotient rule again. Okay, so here, now getting right here, this is chain rule. So remember, this is the power, because this can be rewritten as sec x and then a square. So, you know, and the reason I just rewrote in this form is because we can then use the chain rule. It just maybe it makes this easier for us to use the chain rule. So the power comes down. That's the first thing. Then the derivative of inside. So as I said, sec x differentiates to sec x tan x. And finally, we write the basically the function inside. So tan x. Then the function inside, but the power decreases by 1. We can simplify this, which gives us 2 sec squared x tan x. So this is the second derivative. Now we want to find the point of inflection, so we need to solve the equation f double dash x is equal to 0. So we set this equation equal to 0, which is 2 sec squared x times tan x is equal to 0. So this equation obviously looks a bit nasty, and we don't want to deal with this equation because it's not in the nicest form. What we can do is to rewrite the equation in a different way and then simplifying that. So that's the goal here. So remember that sec x is equal to 1 over cos x, right? So what we can write here instead of 2 sec squared x, we can write 2 over cos squared x. That's just the same thing, right? Because 2 times sec squared is equal to 2 over cos squared x. So that's the first one. And then for the second term, which is tan x, as I mentioned above, tan x is equal to sine x over cos x is equal to 0. Now we can simplify this. So the numerator becomes 2 sine x over cos cube x is equal to 0. And then a simple cross multiplication gives us 2 sine x is equal to 0. And then divide both sides by 2 to get sine x equal to 0. And this is the equation that we need to solve now. And just remember that in this question, x is between pi over 2 and minus pi over 2. And in this domain, the only value of x that makes sine 0 is just when x is equal to 0 itself, right? Because there is no other value in this domain that when x is 0, then the output is also 0. So when x is 0, x is equal to 0 is a solution to this equation. So x is equal to 0. That's the only solution to the equation. So now this is the x coordinates of the point of inflection, or at least we haven't shown that yet, but we know it's ultimately going to be the x coordinate because the question has basically told us that the point of inflection is the origin. So now we need to find a y coordinate and then prove that's the point of inflection at the end. So we just need to substitute x is equal to 0 into f of x to find the value of y, y coordinate. So f of 0 is equal to tan of 0, and tan of 0 is equal to just 0. So the coordinates that we have found so far are the coordinates of the origin, which are 0 and 0. So this is a very important step because now we have the coordinates, but there is one more step left. Because it's a very common error that the students get to this point and say, okay, oh yes, I have found the value, I've got the origin, so that must be the end of my proof. But that's wrong, because we also need to check the behavior of the values with the second derivative, and that way we can prove that's indeed a point of inflection. So how do we do that? As I have shown in the previous videos, if you haven't watched, make sure to watch them because I have done this with different questions and different functions. So there's always a difference between the videos because I don't do two similar videos that are exactly the same. So now what we do here is that, so we know that x is equal to 0. So what we want to find is that f double dash of 0 plus 0 0.1 and also f double dash 0 minus 0 0.1. The reason is that we want to know what's the behavior of the second derivative just before and just after the x coordinate of the point of inflection, because the idea is that if we get a positive value for one of them and a negative value, or in other words two different signs, then that means that's the point of inflection. But if we get two same signs, positive or negative, then that means that's not a point of inflection, because remember, the point of inflection is a point that the curve changes from being concave to convex or vice versa. So that's why there is a change of sign for the second derivative. That's the reason. Okay, now it's the matter of substituting this and just finding the values. So I'm going to use calculator. So for f double dash of 0 0.1, we get 0 0.203 to 3 decimal places, and this is positive, obviously. So we want the second one to be negative in order for it to be a point of inflection. And the second derivative, so f double dash x of minus 0 0.1 is minus 0 0.203, which is negative. Thus, this is the point of inflection. So this is the point of inflection, and that's the end of the proof. All right, that's it, and thank you for watching.